So first thing, we have exam 3, the in-class exam next Monday. Exam 3, a week from today. So 10:30. I have to think a little bit about what topics are going to be on it, but I think it's going to be everything up through Newton's second law. So topics, probably, we'll see like how far we get tonight and stuff like that, through Newton's second law. Does anybody have any questions on homework problems or anything like that? Do you have it with you? Okay. Number 7. Okay, so this is Newton's second law, number 7. And when you look at it at first, it looks kind of crazy. It's sort of intimidating looking before you start thinking about what to do. But there's 150 kilogram mass hanging from cables. Well, hanging from a single cable that's just strung through these pulleys like this. And it's at rest. And we want to figure out what are the 2 force vectors that the cable applies to the mass. We're going to use Newton's second law, so the first thing we have to do is a free body diagram. So a free body diagram of the mass. Yeah, it does give those angles. So we know that this angle is 40 degrees, and this one's 40 degrees. Okay, so here's the mass. The weight acts down. That's 150 times 9.81. So that's 1471.5. And then the cable applies a force that's parallel to the cable away from the chosen body. So one of these forces goes like this, and one goes like this. And since between the 2 endpoints, all that cable does is cross over pulleys, we know that these 2 forces have the same magnitude, so those 2 T's are the same. And so before I go to Newton's second law, let's think about how to represent these force vectors in components. So we have one that goes like this. Put the origin at the tail of the vector. We know that this angle is 40 degrees. And so the angle that you want to use there for sine and cosine is 40. The magnitude is t. So this vector is t times cosine of 40, t times sine of 40. And that comes out to be 0.766 t, 0.643 t. And then the other force vector goes this way. Put the origin at the tail. This angle's 40 degrees. So now the angle that matters for this one, start at the positive x-axis, and you go 180 minus 40. So 140 degrees. And so you get t times the cosine of 140, t times the sine of 140, and that's negative 0.766 t, positive 0.643 t, so Newton's second law says rate is 0, negative 1471.5, and then add those two force vectors we just found, so plus 0.766 t, 0.643 t, plus negative 0.766 t, 0.643 t, and that's equal to the mass times the acceleration. This thing's at rest, so the acceleration is 0. So the x equation says 0 plus 0.766 t minus 0.766 t is equal to 0. What do you get if you add 0.766 t and then subtract 0.766 t? Yeah, so you just get 0 is equal to 0 for the x. Those two cancel out. For the y equation, you get 1471.5 plus 0.643t plus 0.643t is equal to 0. Well, you can add those two together and you get, for the y components, those don't cancel. You get 1.286t is equal to 0. Yep, what? Yes, thank you. And so t then is equal to 1471.5 divided by 1.286. I think I remember that's something like 1144.6 newtons. And so that's the magnitude of the force that cable applies to the things it's connected to. But to get the force vectors, you take that t and plug them back into those force vectors in Newton's second law. So this over here is the force vector applied to the right of the mass, and this is the force vector applied to the left of the mass. All we have to do is plug this value into those. So plug it into this. And this. And then those are the two force vectors. I guess I skipped one step. So I added 1471.5 to both sides, and then I divided both sides by 1.286. Any other questions about that? Okay. So let me do any other homework questions you'd like to see? Here you go. Okay, let's do another table example. So this is one of a type of problem that where you use the fact that these cables don't stretch or contract. And so you know that whatever the motion is of one end of the cable is related to the motion at the other end of the cable. So these cables don't stretch or contract. So often you can relate the motion at two different points on the cable. Okay, so here's the example I'm going to use. So let's say that we have this ledge. There's a cart on the flat part. Let's say that has a mass of 1 kilogram. And then there's a pulley over the corner. And a cable goes over the pulley that connects the 1 kilogram mass to a hanging mass. Let's say this is 0.2 kilograms. And we want to know what the acceleration vector is of the 1 kilogram. Well, let's calculate two things. So the acceleration vector of the 1 kilogram cart. And second, what's the cable tension? Okay, so the way I'm going to approach this is I'm going to first isolate the 1 kilogram cart, use Newton's second law, and see what we can calculate. What we're going to see is that that's not enough information, and it sort of makes sense that it wouldn't be, because so if we isolate the 1 kilogram cart, we don't have any reason yet to know what the mass is here. You know, if you put a 50-pound mass on the end of this, this is all going to behave differently than if you put a 1-pound mass there, right? So it sort of makes sense that we would have to take both of those into account. And so then we're going to isolate this, and it's going to give us another set of equations. What we're going to have to do is we're going to have to come up with a relationship between the acceleration of the cart and the acceleration of the mass. Okay. And here's how we're going to think about it. Instead of thinking right away about it in terms of accelerations, just think about it in terms of motions. Let's say that you pull this cable, this mass down 1 inch. Where would the cart go? Right. Yeah, so if this goes down 1 inch, that goes to the right 1 inch. Okay, and if that one goes to the left 1 inch, that one goes up 1 inch. Okay, and so because those motions are sort of locked to each other in that way, whatever the velocity is of this going down, that has to be the velocity of this going to the right. And also whatever the acceleration of this is going down, that's the acceleration of this going to the right. So that's the idea we're going to use. Whenever you see these, you can always just think about it, even though it's acceleration we're dealing with, you can always just ask yourself, if I pull this one 1 inch, where does this one go? Okay. All right, so we'll start with a free body diagram of the cart. there's a weight force going down. So that's 1 times 9.81, so 9.81 newtons. And then there's a pushing force from the floor up on the wheels. I'll call that N. And then there's a pulling force from the cable going this way. I'll call it T. We don't have any way to know what that is yet. And so then we'll go to Newton's second law. And Newton's second law says 0N plus 0, negative 9.81 plus T0 is equal to the mass of the cart times its acceleration. The mass is 1, and we've done this before. What do we know about the acceleration? All we have to figure out is it moving in the x direction, along the x-axis, or along the y-axis? This is moving along the x-axis, so I'm just going to write this as A0. And I would do that even if you looked at this picture and it was obvious that it was going to move in the negative x direction. That's okay. The math will figure out that sign on its own. All you have to do is figure out, am I dealing with x or y? Okay, so we have two equations. The x equation says 0 plus 0 plus t is equal to a. So I'll just write that as t is equal to a. And the y equation says n minus 9.81 is equal to 0. From the y equation, you can see right away that n is equal to 9.81. But that doesn't help us with anything. That wasn't asked for in the problem. If the problem happened to ask for the normal force, then that would be something you wanted. But what is useful is this. We know that whatever the cable tension is, it's equal to the acceleration of that cart. It's useful, but we can't use it to solve for anything yet because we right now have one useful equation with one useful equation with two variables. And you can only solve for one variable for each equation you have. So as far as we know from this, 1 meter per second squared, or T could be negative 50 newtons and A could be negative 50 meters per second squared. So we're going to have to narrow it down more. And the way we're going to do that is isolate the hanging mass. Okay, so free body diagram of the mass, hanging mass. So the forces on that are a weight force. That's 0.2 times 9.81, so that's 1.962. And then there's an upward force from the cable. We know it's in this direction. Do we know anything about its magnitude? It's T. It has to be the same magnitude as the other one. And before I go to Newton's second law, yes? 0.2 kilograms. 0.2. So before I go to Newton's second law, let's think about what we know about the acceleration. So we need to come up with an acceleration vector that's related to this acceleration vector of the cart. And we already figured out that if the cart's accelerating to the right, say 1, 0, the hanging mass has to accelerate down with a magnitude of 1. So if this has an acceleration, the cart has an acceleration of a0, what would be the acceleration of the hanging mass? 0, negative a. Because like, think about this being a positive number. That means the acceleration of the cart is going to the right. And that means that the acceleration of the thing of the mass has to be in the negative y direction. Any questions about that?
So if it was going to,
Mm-hmm.
would it be 1 negative 0? If the cart was going to...
Yeah, so let me write down this formula and then let's think about a couple scenarios. So the acceleration vector of the mass is going to be 0, negative a. And let's just think about how that works. So when we solve this, in some cases, you'll calculate that a is negative. Okay? So what that would say is that, so let's say we did this calculation and got that a is equal to negative 2. So a is equal to negative 2. That means the acceleration of this thing is negative 2, 0. Okay, so that means this is accelerating in the negative x direction. Okay. And if you plug negative 2 in here, you get a negative of a negative 2. So you get an acceleration of 0, positive 2. And that means that the mass accelerated up. And that's the relationship you want. If this one accelerates to the left, this one has to accelerate up. Okay. And if you put in a positive number, then each one of those directions switches. If a is equal to positive 2, then this cart's accelerating to the right. Put a positive 2 in here, that says this mass is accelerating down. So that's the relationship we want. So one thing you can do is you can just, try a couple of formulas that seem like they make sense, and then try a couple cases, plug in a positive value, a negative value, and make sure that those objects are moving with the relationship that you want. Okay, so now Newton's second law says 0, positive t plus 0, negative 1.962 is equal to the mass times the acceleration vector, 0, negative a. And that gives two equations. The x equation says 0 equals 0, so that definitely doesn't help. The y equation says t minus 1.962 is equal to negative 0.2a. And so now this one and this one, those two red boxed equations, are a system of two equations for two variables, and you can solve it. Okay, so two equations for two variables. First one was t is equal to a, and the second one says t minus 1.962 is equal to negative 0.2a. You can always solve these by substitution, so let's just let's take the, equation 1 says that anywhere there's a t in equation 2, we can substitute an a. So let's say that a minus 1.962 is equal to negative 0.2a. And now add 0.2a to both sides, and you get 1.2a minus 1.962 is equal to 0. I'll just do that over here. So 1.2a is equal to 1.962. And then can someone divide 1.962 by 1.2? 1.635 meters per second squared. We weren't looking for the magnitude of the acceleration. We were looking for the acceleration vector of the cart. So now we just take this number and plug it back into the acceleration vector of the cart. Here, we know everything about this acceleration vector, except we don't know what that variable is. Well, now we figured it out, so plug it in there. And you get that the acceleration vector of the 1 kilogram cart is equal to 1.6350 meters per second squared. Or another way to think about that is 1.635 meters per second squared Yep. Up. Yeah. I figured you didn't want me to scroll down. Get it out of my sight. I can't look at it anymore. Okay, we still have to figure out T. Well, that's pretty easy in this case because so we figured out that A is 1.635. Equation 1 here says that T is equal to A, so T is equal to 1.635 newtons. And so, that could be useful in figuring out how strong the hook has to be that connects the cable to the cart, or in figuring out how strong of a cable you need to use, like what kind of, fishing fishing line is sold by the amount of weight it can hold, right? I know it has a weight associated with it. I assume that's like roughly the amount of weight it can hold, the amount of force it can hold. So you'd have to find a line that can support 1.635 newtons of force. And engineering-wise, that stuff's important because the stronger and the heavier you make something, the more expensive it is to make, for the most part. So you can understand why that would be a useful analysis for a company that's trying to make these things useful, but still as cheaply as they can. Any questions about that problem? Okay. Let's do another similar one. So let's say this time there's a pulley hanging from the ceiling. And let's say on this side we have a mass of 10 kilograms. And on this side we have a mass of 20 kilograms. And we want to calculate the same two things. Let's say the acceleration vector of the 10 kilogram mass. And second, the cable tension. well, what's going to happen here, you have a heavier thing here and a lighter thing here. So the heavier thing is going to accelerate down, the lighter thing is going to accelerate up. Anybody have like any intuition? You know, don't worry if it's right or wrong. Anybody have a guess at what that cable tension is going to be? I mean, yeah, you know, that's I don't think that's right, but that's a good sort of way to think about it. Like you might sort of think, well, first you have to think about it in forces instead of in masses. But you know, this one's applying a force on that cable of 98.1 newtons. This one's applying a force of 196.2 newtons on the other end. And you might think, well, these are hanging from it, so it's going to be, you know, one of those two weights or maybe somewhere in between. And yeah, it's going to turn out to be somewhere in between those two forces. Okay, so let's start by drawing a free body diagram of the 10 kilogram. The forces on it are gravity, so that's 98.1 newtons down. And then a cable tension up. So Newton's second law says 0, negative 98.1 plus 0t is equal to the mass times the acceleration vector. So for this first one, all we have to do is decide, is this going to accelerate along the x-axis or the y-axis? Right, so I'm just going to call this 0a. And the signs will work out for themselves. We just have to choose which component we're dealing with. So the x equation doesn't help, 0 equals 0. The y equation says negative 98.1 plus t is equal to a. That one gives us a useful relationship, but we can't solve it yet because that's one equation with two variables. So I'll set this aside. Question? Yes, thank you. And then go the 20 kilogram mass. The weight force is 20 times 9.81, so 196.2. And the cable applies an upward force of T. So Newton's second law says 0, negative 196.2 plus 0T is equal to the mass times the acceleration vector. And so now we have to think about the relationship between the acceleration of the 10 and the acceleration of the 20. So if the 10 kilogram mass accelerates, and don't think of it as acceleration, think of it as position. So if this one moves up 1 inch, where does this one go? Down the same amount, right? Down 1 inch. And if this one goes up 1 inch, this one goes down 1 inch. So anybody have an idea what that relationship would be between those vectors? Well, if this one has an acceleration, so I think the way to do it is to always think this A is positive. Okay? So if this one has a positive value of 1 or something, this goes has an acceleration up of 1. This one has to have a downward acceleration of 1, and so the vector has to be 0, negative a. So 0, negative a. The x equation doesn't give anything, but the y equation again gives 196.2 plus t is equal to negative 20a. So we have two equations for two variables. The first one says negative 98.1 plus t is equal to 10a. And the second one says negative 196.2 plus t is equal to negative 20a. You can do it by substitution again. I think that's probably the way to do it. So from this first one, I'll say t is equal to 10a plus 98.1. And then I'll substitute it into the second one. So we get negative 196.2 plus the quantity 10a plus 98.1 is equal to negative 20a. And so we get negative 98.1 when you add the negative 196.2 and the positive 98.1 is equal to negative 30a. So what's 98.1 divided by 30? 3.27 meters per second squared. And then plug that back into the acceleration from Newton's second law, and you get the acceleration for the 10 kilogram is equal to 3.27. And then for t, we can go back to any one of these equations that works out nicely. I guess let's go. One right here has t isolated, so we just have to plug in 3.27 for a. So we get 32.7 plus 98.1 is 135.8. Still got it. Okay, so T is equal to 135.8 newtons. And that is somewhere in between, just about like you guessed, that force is somewhere in between the weight of a 10 kilogram thing and the weight of a 20 kilogram thing. Not exactly in between. Right. Yep, exactly. Yep. Yep, that's in the right ballpark. So as long as if you haven't made any mistakes in your calculations, every equation you have sitting around here is a true equation. So you can just find whichever one makes it easiest to calculate the other one. So I just used the one that already had T isolated. Okay, so that was an example of how to do this, but we also saw something that I guess we all would have known beforehand, and that's that 10 kilogram mass cannot hold up a 20 kilogram mass, right? That's what that acceleration tells us. If you left a 10 kilogram mass here, like you had to go to the bathroom, you were holding up this 20 kilogram, and you're like, well, I'm in the bathroom, you're in charge, you hold up this 20 kilogram mass. This would not do it. You know, you lose your job. And so, okay, so now that goes into the next thing that I want to bring up. That's the idea of pulley advantage. Have you heard that term before? So, I remember like being a kid and we had this tree house and there was a pulley and my parents like mentioned something about like, yeah, like this pulley makes it like easier. Like you can, by applying the same amount of force, this pulley lets you lift up things, you know, like do the work of being able to apply more force. You know what I'm talking like? Sort of this vague idea that like a pulley makes it possible with the same amount of force applied to lift heavier things. Okay. And so when I first took physics, I was surprised to find out that all a pulley really does is change the direction of this cable force. It's like, hey, a pulley doesn't really do that at all, you know? Like a pulley doesn't. So, like I would have thought going into physics, like, oh, because of this pulley, maybe this 10 kilogram mass can hold up this 20 kilogram mass, you know? Pulley advantage. Well, there is such a thing as pulley advantage, but it's not just a single pulley that does it. It's a sort of a smart configuration of multiple pulleys that allows that to happen. So now I want to do the same problem, but with two different pulleys, and we'll see how you can rig them up to use pulley advantage so that in this next example, the 10 kilogram mass really is going to hold up a 20 kilogram mass. Did I do this whole lecture last time?
I just didn't know if we all.
Well, I wanted to. Okay. Well, let's do something else then. Pretty interesting, though, still. Okay.
I'm sorry, people.
No, look at last week's notes. Okay, no, I'm sorry about that. I was thinking that I went through this in the day class. What? Well, maybe we should go to something new that we haven't already talked about. Oh, oh, and you guys were too nice to tell me. One, yeah, sure is. Okay, so now's a good time. Anybody who has anything wants to tell me about any mistakes I made, let's get them all out right now and then. Okay. Well, anyways, pulley advantage is cool still. Okay, so the next thing I want to talk about. So what are the force types? What did I call these before? Contact force types. So the first one is pushing. Second one is pulling. And the last one is friction. I haven't talked about friction yet. Thank you. So we've done both of these now, and now we're going on to the last one, friction. Okay, so friction. There's two types of friction. So there's what's called static friction and dynamic friction. So let me just demonstrate what those both are. So static friction is, so friction always happens when two surfaces are sliding against each other. Or trying to, I guess, if it's static, also if they're like, there's something, if it's preventing two things from moving relative to each other. So static friction, if we ignore so there's a downward force of gravity and an upward normal force on the stapler right now. And if I apply, so right now I'm applying a small horizontal force trying to push this thing this way. Okay. I'm not pushing very hard, but if this was ice or, an air hockey table, this little force would make this accelerate a little bit this direction. The reason it's not accelerating that way is because the force that my finger's applying in that direction is counteracted by another horizontal force that the table's applying to this thing in the other direction. And they're exactly equal and opposite. So the thing doesn't go anywhere. Newton's second law says no acceleration. But so that was a really small horizontal force. Let's say I applied 1 Newton of force this way, and the table applied 1 Newton of force the other way, so there was no acceleration. We know it didn't apply 4 Newtons of force that way, because then I would push it that way and the thing would accelerate back, and that would be super weird. But so now I'm going to apply a different force. Now say I'm applying 2 Newtons of force. And now the table's applying exactly 2 Newtons of friction force back the other way to still keep it from accelerating. So static friction is whatever it's, when the things are not sliding relative to each other, the friction is applying whatever force is necessary to keep it at rest. That's sort of a weird thing, but that's how it works. So static friction provides the force necessary to prevent motion from starting. Dynamic friction then is, eventually the friction, it's not an unlimited amount of force that static friction can apply. And if I push a little bit harder than I was before, it starts to move. And then you're in the dynamic case where, so I'm applying a force to this. Think about it like this. I'm applying a force. But there has to be another horizontal force acting or this would be accelerating. And you can see it's moving at a constant speed with, moving with a constant velocity. So there has to be another force that's applied in the other direction. And that's dynamic friction or kinetic friction. I don't even know if it's called dynamic friction. Don't write that. I meant kinetic friction. Let me think. No, not really. We'll talk about energy later. Okay, so kinetic friction is the force applied to an object while it's sliding. There is a big similarity between these two types of friction in the way you calculate them. For static friction, the force of friction applied by static friction is whatever is required up to a sort of a threshold value that's equal to this constant. That's Greek letter mu, but it's just a constant time sub s. So this is mu, the static coefficient of friction times the normal force. So right now there's some amount of normal force applied to the stapler by the table. And there is a coefficient of static friction between whatever kind of metal this is and whatever surface this table has. You could look that up. And that'll tell you for this normal force, what's the maximum friction force this can apply before I start to make it move. Okay. And it's less than or equal because, like we saw, that friction force can change depending on how much force is being applied to try to make it move. Kinetic friction, once it starts sliding, the force of kinetic friction, FF is force of friction, is always, it's not up to a certain value, it's always equal to the constant of kinetic friction, that's mu sub k, times the normal force. So both of these two constants are properties of the two materials that are sliding relative to each other. We are not going to deal with this one just to save a little time in this section. We're only going to deal with this one. But doing the calculations isn't too much different. There's one more thing that I want to say about these. So with static friction, that force of friction is up to a certain value. With kinetic, it's always equal to a certain value. But then the two expressions look pretty much the same. But notice that they have different constants. You might think that if you look up the coefficient of friction for, I don't know what that is, steel, and for mica, you would get a single value that you could use in both of these. But in fact, this is always bigger than this one. Static friction can always, for any two materials, produce a bigger force than kinetic friction does. So mu sub k is always smaller than, let me put the order here. Mu sub s is always bigger than mu sub k. And that just has to do with the way friction happens. There's little microscopic imperfections that sort of ooze into the little nooks and crannies. And if those two things are still just sitting next to each other, they develop this grip on each other that you have to break before they start sliding. Okay, so kinetic force of friction. It's a force, so that means it's a vector. We need to know the direction and the magnitude. So first, the direction is always opposite the direction of motion. Or in other words, it's always opposite the direction of the velocity vector. And the magnitude is always equal to that kinetic coefficient of friction times the normal force. Where that constant mu sub k depends on the two materials in contact. Okay, so let's see how this works. Yeah. Materials, MAT''LS. So let's go back to the example of the cart and the hanging mass. But this time, the cart is a box with a coefficient of kinetic friction of 0.2. And at the instant of our calculation, the box is sliding to the right. Okay, so you still have the pulley there, but now this is a box with a mass of 1 kilogram. And this has a mass of 0.2 kilograms. So when we did this problem without friction, what happened? Yeah, it had this accelerated this way. What was the main 1.635? Is that one? So this had an acceleration this way of 1.635 meters per second squared. And so now we're going to see, now that we've added friction, here are the possibilities of what could happen. So first, it could still be accelerating this way, but just with a smaller acceleration than 1.635. Or it's possible that the acceleration will be, that the force applied to this box by the friction going this way is bigger than the force of the cable pulling it that way. And in that case, this thing, even though it's moving to the right now, will be slowing down and until eventually it would stop. Does that make sort of intuitive sense of those two possibilities? Okay, so the velocity is this way. And so let's go through this problem the same way. So first, a free body diagram of the box. What are the forces? There's a downward force of 1 times 9.81, so 9.81 newtons. There's a cable force of T going this way. There's a normal force pushing up. And this time there's a fourth force, a force of friction, that goes in the opposite direction of the velocity vector. So it goes to the left, and it has a magnitude that's equal to mu sub k times n. Well, we know what mu sub k is, so I'll write that as 0.2. Any questions about that yet? Okay, so Newton's second law says 0, negative 9.81 plus 0n plus t0 plus negative 0.2 n0 is equal to the mass times the acceleration. Is the acceleration in the x, along the x-axis or the y-axis? Yeah, so that's still just a0. Okay, so the x equation says e minus 0.2n is equal to a. The y equation says negative 9.81 plus n is equal to 0. So the y equation here tells us that n is equal to 9.81 newtons. When we did this example before without friction, remember what we did with the y equation here? Anyone remember? We just threw it away. We used this one, but this didn't have any stuff we needed. So this was the only one we kept. Okay. Now though, because the horizontal component has that friction force in it, which has the normal force in it, we need to use that y equation in here. Like right now, this equation has 3 variables. We want to get it down to 2. And so we'll use what we can figure out from the y equation about n and plug it in there. So if we combine these two, we get t minus 0.2 times 9.81. So that's 1.962 is equal to a. And then this is the equation that we'll hold on to for later. Any questions about that? Okay, so now the other one doesn't change. The free body diagram of the hanging mass is still the same. We just have a downward force of 1.962 and an upward force of T. So Newton's second law says 0, negative 1.962 plus 0T is equal to the mass times, what do we know about the acceleration? So if the block moves an inch in the positive x direction, the hanging mass moves an inch in the negative y direction. So this is 0, negative a. So the x equation says 0 equals 0 again. The y equation says negative 1.962 plus t is equal to negative 0.2a. And so there's our system of two equations for two variables. The first one says, I guess I'll write it as t is equal to 1.962 plus a. And the second one says negative 1.962 plus t is equal to negative 0.2a. And so I'll substitute the first one into the second one. Negative 1.962 plus the quantity 1.962 plus a is equal to negative 0.2a. These two things cancel out. And you get 1.2a is equal to 0. A is equal to 0. Well, that's sort of boring. That happened because I chose the coefficient of friction to be the same as the mass of the hanging mass. But so what does that say if, so we know that at the start, this has a velocity to the right. Okay. That's given as part of the problem. If we know that the acceleration is 0, that means that this will just keep moving at whatever that initial velocity was. It'll keep moving with that velocity to the right. Okay, so it's not speeding up or slowing down. It's just exactly balanced. The same idea is like when I push on this with enough force that it just keeps moving at a constant velocity. The friction force and the force I'm applying to it are exactly balanced. Any questions about that? Okay. So we'll do more examples next time. There's one more thing I want to say. So from now on, anytime an object is sliding or rolling, along a surface. Choose the y-axis pointing directly out of the surface. So for example, if you have a problem like this, there's a force applied there, this is an incline. The coordinate system you want to choose has the y-axis pointing out of the surface like that, and the x-axis pointing that way. The benefits of doing that, there's no reason you have to do that, but here are the benefits of doing it. First, the acceleration vector only has an x component all the time. Second, the normal force is always just a positive y component. And then third, the force of friction only has an x component. If you didn't choose this rotated coordinate system, each one of those forces, you'd have to use cosine and sine and figure out the angle and do all that stuff. There's one drawback. And that is that choosing a rotated coordinate system like that messes up the simplicity of the weight force. So now you need to use cosine and sine to calculate the weight force vector. So that's kind of a pain. The thing that was always the simplest one to deal with before is now the most complicated one. But you can see why we're doing this. We get 3 pros and 1 con, so overall it helps. So on Wednesday we'll do some examples of these. All right, that's all.